Hi everyone, today we will be looking at ionization energy. I will start by explaining all the main concepts and then answering some practice questions at the end. The learning objectives for today's video will be to know the definition of ionization energy, be able to write the ionization energy equations for different ionization energy numbers, so the first, second, and third ionization energies and so on, describe ionization energy trends going across any period in the periodic table, thoroughly explain the reasons for any exceptions to the ionization energy trends across a period, describe ionization energy trends going down any group in the periodic table, and explain how the existence of main and sub-energy levels can be proven from trends in ionization energies across a period. So let's make a start then. Remember, the sections highlighted in blue are just there to help you understand the concepts more easily, but please pay attention to the whole thing so that you can fully understand the concepts I'm trying to explain. Let's start by looking at some background knowledge. Atoms have the same number of positively charged protons and negatively charged electrons, just like the oxygen atom opposite. Atoms therefore have an overall charge of 0, because if we look at this oxygen atom opposite, we can see the different subatomic particles and the main energy levels. If you're not familiar with this, I suggest you watch the previous videos in this series. The blue crosses represent the negatively charged electrons. The red circles with the plus sign inside represent the positively charged protons, and the green circles with the zeros inside represent the neutrons, which have a charge of 0. These white circles represent the main energy levels. So if you didn't know, in an atom, electrons orbit what's known as the nucleus of the atom at certain main energy levels, and each main energy level can hold up to a certain maximum number of electrons. And at the center of the nucleus we have a cluster of positively charged protons and neutrons that have no charge. So the nucleus is considered to be positively charged because the only positively charged subatomic particles, that's what these are called, electrons, protons, and neutrons, are called subatomic particles. The only type of charged subatomic particles in the nucleus is the proton. That's why the overall charge of the nucleus is positive, and the atom is held together by the electrostatic forces of attraction between the outer electrons and the positively charged nucleus. Again, if you need help on this, watch the previous videos. From this we can see that the oxygen atom has an overall charge of 0, because counting the negatively charged electrons gives us 1, 2, 3, 4, 5, 6, 7, and 8. So 8 electrons, and then the number of protons, 1, 2, 3, 4, 5, 6, 7, 8 protons. We don't count the number of neutrons, although we could to find the MR, but we don't because neutrons have a charge of 0. When we say relative charge, we're comparing the actual charge of the electron, the actual charge of the neutron, and the actual charge of the proton with the actual charge of the proton. So the actual charge of the neutron is 0, but the actual charge of an electron is negative 1.19 times 10 to the negative 19 coulombs, and the charge of a proton is plus 1.19 times 10 to the negative 19. The charge of a proton and the charge of an electron are in a 1 to negative 1 ratio. So the relative charges for electrons is negative 1, for protons it's plus 1. So now to find the overall charge of the oxygen atom, we do negative 8 because we have 8 electrons, and then each electron has a relative charge of negative 1. So negative 8 plus 8 because we have 8 protons, and each proton has a relative charge of plus 1. So negative 8 plus 8 gives us 0, hence why the oxygen atom has an overall charge of 0, and this is the reason why all atoms have an overall charge of 0. You would do the exact same thing we've done here with any other atom, whether it be fluorine, carbon, sulfur, phosphorus, whichever. Ions are atoms that have an unequal number of protons and electrons, and so they do have an overall charge. The size of the charge depends on how many more protons or electrons there are. Ions are atoms that have an unequal number of protons and electrons, and so they do have an overall charge, and the size of the charge depends on how many more protons or electrons there are. So if we had an atom containing 2 more protons than it did electrons, that atom would be positively charged and it would have an overall charge of plus 2. If we had another atom which had 3 more electrons than it did protons, that would be a negative ion with an overall charge of 3 minus, or negative 3. An atom can lose or gain electrons for reasons we'll look at in upcoming videos to form positively or negatively charged ions respectively. An atom that loses electrons becomes positively charged because we have more protons than we do electrons, and an atom that gains electrons electrons will become negatively charged because there will be more electrons than protons. Energy must be supplied in order to remove an electron from an atom. So this is an endothermic process. An endothermic process or an endothermic reaction is a chemical reaction or a chemical process that takes in more energy than it releases. This is related to the energetics topic and is something we will look at in more detail in upcoming videos. The term enthalpy change refers to the heat energy change measured under constant pressure and temperature. And these conditions are referred to as standard conditions that are a pressure of 100 kilopascals. 100 kilopascals is the atmospheric pressure at sea level, and a temperature of 298 Kelvin, which is room temperature. 298 Kelvin is equal to 25 degrees Celsius. Now let's look at the definition of ionization energy. So ionization energies can be classed into first, second, or third ionization energies, and so on, depending on the number of electrons in the atom. So if we had, as in the case of this fluorine atom, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. So there will be 9 ionization energies. First ionization energy is defined as the enthalpy change when 1 mole, in case you didn't know, 1 mole is the amount of a substance containing 6.022 times 10 to the power 23 particles. And this is something related to stoichiometry and to number of moles calculations, and there'll be a whole series on that very soon. So it's defined as the enthalpy change when 1 mole of electrons is removed from 1 mole of gaseous atoms to form 1 mole of gaseous ions, each with a single positive charge. The starting atoms and the product ions have to be in a gaseous state. And the ionization energy symbol can be seen opposite. So this is the ionization energy symbol. We will make use of these symbols heavily, especially in energetics. There will be a number of series on energetics and thermodynamics coming soon. For the second ionization energy, 1 mole of electrons are removed from 1 mole of gaseous 1+ ions instead of gaseous atoms. Ionization energies occur successively. So the second ionization energy can't be measured if the first ionization energy was not measured. So the second ionization energy can only take place if the first ionization energy took place. So that's why when the second ionization energy takes place, 1 mole of electrons are removed from 1 mole of gaseous 1+ ions, because the gaseous 1+ ions were the product of the first ionization energy, and we just said the second ionization energy can only happen if the first ionization energy happened first. So that's why for the second ionization energy, 1 mole of electrons are removed from 1 mole of gaseous 1+ ions instead of gaseous atoms. In more simple terms, you can think of it as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions, each with a single positive charge. So the first ionization energy is the energy required to remove the outermost electron in an atom. So the electron furthest away from the nucleus of the atom. In the case of this fluorine atom here, it would be this electron. The second ionization energy is the energy required to remove the second outermost electron, i.e. this one. And the third ionization energy would be the energy required to remove the third outermost electron from the atom, which in this case would be this one. When it comes to deciding the first, second, third, or fourth outermost electrons using a simple dot and cross diagram, don't worry about which electron on the outermost shell you pick as the outermost electron. The important thing is you pick an electron on the outermost shell. So this shell here is the outermost shell. So make sure you pick an electron from the outermost shell. Most textbooks select the electron that isn't paired. I do the same. Pick the outermost electron as the one that isn't paired. For the rest, it really doesn't matter which one you pick as the second, the third, or the fourth. I say it doesn't matter when you have a diagram with chemical symbol or a nucleus surrounded by just main energy level. So if you have a simplistic diagram like this, as long as the outermost electron you pick is on the outer shell or the outer main energy level. However, if there was some kind of representation of sublevels and orbitals, it does matter. And in that case, you would need to make sure you pick the outermost electron. So if you had a 3p sublevel and a 3s sublevel, you would pick the outermost electron from the 3p sublevel, not the 3s sublevel, because the 3p sublevel is further away from the nucleus and therefore higher in energy. And then once all the electrons on the outer main energy level have been accounted for, you can then take into account the electrons on the inner main energy level, or the first main energy level. And if you had 3 main energy levels, you would start with the third, then go to the second, and then to the third. So you can see here we started with 1, 2, 3, and then 4, 5, 6, 7 before moving to the 8th. The 8th outermost electron is on the first main energy level, because we start by counting the ones on the outside first. All ionization energies are measured in kilojoules per mole, and ionization energy has the abbreviation IE. So the abbreviation IE is used in this symbol, and if you wanted to specifically represent the first ionization energy, you can write 1 and then ST to represent first before the IE here, or you could write second, so you would write 2 and then ND to represent the second ionization energy, and then you could also do the third, 3 and then RD right here just before the IE, and that would show which ionization energy you're talking about. It's really important to remember the second ionization energy can't happen unless the first one has happened, and the third ionization energy can't happen unless the first and the second ionization energies have happened, and so on. It's really important you remember this point. Now let's look at ionization energy equations. So to write ionization energy equations, you must write both the starting atoms or ions and the product ions with the gaseous state symbol as shown opposite. So you write the gaseous state symbol by writing a G inside brackets. That's what we use to represent the gaseous state symbol. There are also other state symbols which we'll look at in upcoming videos. There's the aqueous solution state symbol, there's the solid state symbol, there's also the liquid state symbol. But in this case we're using the gaseous state symbol, and this is how we represent it. So we need to represent the starting atoms or ions and the product ions using gaseous symbols. You don't need to represent the electron removed using a gaseous state symbol. And this is in accordance with the definition for ionization energy, which states that it is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions to form 1 mole of gaseous ions. From these equations you can see that 1 mole of electrons has been removed from 1 mole of gaseous atoms or ions. They can also be ions for second ionization energies and greater, and again 1 mole of gaseous ions are formed. Equation number 1 opposite shows the first ionization energy for a lithium atom. So this is a lithium atom. Atoms have an overall charge of 0. So 1 mole of electrons has been removed from 1 mole of gaseous lithium atoms, and we've obtained 1 mole of gaseous lithium ions. And this plus electron is the electron that was removed from the lithium atom. Equation number 2 opposite shows the second ionization energy for a lithium atom. This time the electron is removed from a lithium ion. So we said before that the second ionization energy can only happen if the first ionization energy happens. So after the first ionization energy, we're left with a lithium plus ion. And the second ionization energy is the energy required to remove the second outermost electron from a lithium atom. And when the second outermost electron is being removed, it's being removed from a lithium plus ion. So we are left with a lithium 2 plus ion plus 1 electron, this plus electron coming from the electron that was removed from this lithium plus ion. Equation number 3 shows the third ionization energy for a magnesium atom. The electron is removed from a magnesium 2 plus ion because the third outermost electron can only be removed if the first two have been removed. So the third ionization energy can only happen if the first and second ionization energies have happened first. So for the third ionization energy, 1 mole of electrons is being removed from 1 mole of gaseous 2 plus ions. So 1 mole of magnesium 2 plus ions will give us 1 mole of gaseous magnesium 3 plus ions plus 1 electron. And this is the electron again removed from the magnesium 2 plus ion. The equation marked with a star should not be confused with an ionization energy equation, because the ionization energy is the energy required to remove only 1 mole of electrons, not 2. So here 2 moles of electrons have been removed, not 1, and that contradicts the definition. Instead, this equation marked with a star is a half equation. We'll talk more about that in upcoming videos, and this shows how a magnesium atom becomes a magnesium ion. Basically, the crux of the matter here is that certain atoms of certain elements need to gain or lose a certain number of electrons to form stable ions with an electron configuration identical to that of a noble gas atom. Once they obtain an electron configuration identical to that of a noble gas atom, they have a stable electron arrangement. Hence why atoms have a drive to either lose or gain electrons depending on whether they're metals or non-metals. And this is a topic we'll look at, like I said, in more detail. For magnesium, it has to lose 2 electrons to form the stable Mg2 plus ion. It forms an Mg2 plus ion because magnesium is in group 2, and the reason magnesium is in group 2 is because it has 2 outermost electrons. So it's easier for magnesium to lose those 2 outermost electrons and form 2 plus ions. So now let's look at the ionization energy trends across a period, from left to right. As a general trend, ionization energies increase for the atoms of the elements going across all periods. And periods are horizontal rows in the periodic table. So an example of a horizontal row can be from lithium all the way to neon, from sodium all the way to argon, from potassium all the way to krypton. These are rows in the periodic table, and these are the periods. So the first row is called period 1, the second row is called period 2, the third row is called period 3, the fourth row is called period 4, and so on. So this is because the nuclear charge, which is the number of protons in the nucleus, of the atoms of the elements going across a period increases. And since the number of protons increases, the electrostatic forces of attraction between the positively charged nucleus and the outer electrons increases as well in the atoms of the elements across a period. The energy required to overcome the increasing electrostatic forces of attraction and remove the outer electrons therefore increases for the atoms of the elements across a period. Hence why all ionization energies generally increase. The atomic shielding, which is the number of main energy levels or shells in an atom, and again, if you didn't remember from the previous slide, these shells are what hold the negatively charged electrons which orbit the nucleus. The atomic shielding is the same in the atoms of the elements on the same period. So let's take the example of period 4. Calcium will have the same number of main energy levels as germanium, and bromine will have the same number of main energy levels as potassium because they're on the same period, and the same applies to period 3. Sodium will have the same number of main energy levels as aluminium. For period 3, that's 3 main energy levels. For period 4, that would be 4 main energy levels. And for period 2, lithium, beryllium, boron, carbon, nitrogen all have 2 main energy levels. Same for period 1 and for period 5 and so on. It should also be noted that the atomic radius of the atoms of the elements going across a period decreases due to the increasing electrostatic attraction between the positively charged nucleus and all the surrounding electrons in atoms. It should also be noted that the atomic radius of the atoms of the elements going across a period decreases due to the increasing electrostatic attraction between the positively charged nucleus and all the surrounding electrons in atoms. So across period 3, for example, the atomic number is increasing. The atomic number refers to the number of protons in the nucleus of the atom. That's the same as the nuclear charge. The naming is slightly different, although they mean the same thing, because nuclear charge is referring to the charge of the nucleus of the atom. Because if you recall, the only type of subatomic particle in the nucleus of the atom is the proton, and the proton is positively charged. Neutrons have no charge, so that's why protons have an overall positive charge. The size of this overall positive charge depends on the number of protons. But just remember, nuclear charge and atomic number are basically the same thing. So the atomic number, or the number of protons in the nuclei of the atoms of the elements going across period 3 and any other period, increase. So the electrostatic forces of attraction between the positively charged nuclei and the outer electrons is going to increase for the atoms of the different elements going across the period. So that greater electrostatic attraction means that the surrounding electrons, not just the outer electrons but all the electrons, are closer to the nucleus the greater the nuclear charge. So for period 3, the element sodium has the lowest atomic number and therefore has the greatest atomic radius because it has the weakest electrostatic attraction between the positive nucleus and the outer electrons. Sodium also has the lowest first ionization energy because it has the lowest atomic number and therefore the weakest electrostatic attraction between the nucleus and the outer electrons. Chlorine, however, has the greatest atomic number, therefore the greatest nuclear charge. So it has the greatest electrostatic forces of attraction between the positive nucleus and the outer electrons, and for that reason the atomic radius for chlorine atoms is the shortest of all the elements in period 3 because the outer electrons are closer to the nucleus, and also for that reason the first ionization energy is the greatest, and also for that reason chlorine atoms have the greatest first ionization energy in period 3 because of the greater electrostatic attraction between the positive nucleus and the outer electrons due to the greater nuclear charge. So more energy is needed to overcome this greater electrostatic attraction. So the trend is atomic numbers increase, so therefore the ionization energies increase as well, and the atomic radius decreases across period 3. Now let's look at the first ionization energy graph for period 3. So on the y-axis we have first ionization energy in kilojoules per mole, and on the x-axis we have the atomic number. Going across any period, the atomic number or the nuclear charge will always increase because successive elements in the periodic table increase by 1 atomic number each time, in case you didn't know that. In a period, the atomic number increases from left to right, not the other way around. So you'll see here that generally speaking there's an increase in the first ionization energy across period 3. You can see that sodium has the lowest first ionization energy and argon has the greatest first ionization energy. But you will notice 2 particular exceptions. First being magnesium and aluminium, and the second being phosphorus and sulfur. The magnesium and aluminium exception is noticeable, but the phosphorus and sulfur exception is also there, although it's much smaller. In fact, sulfur has a lower first ionization energy compared to phosphorus by only 2 kilojoules per mole. But nonetheless, these are still deviations from from the overall trend we established before. So we need to understand why these exceptions happen, and we will explain these using sub-energy levels and orbitals. Now let's look at the first exception to the first ionization energy trend across period 3. So in period 3 of the periodic table, there are two exceptions to the trend of increasing ionization energies across a period. These exceptions can generally be applied to the elements in mainly period 2, but also to varying extents in other periods that are in the same position on the period as the elements magnesium, aluminium, phosphorus, and sulfur in their own period. So in other words, elements like beryllium, boron, nitrogen, and oxygen for period 2. And then for period 4, we're talking about elements like calcium, gallium, arsenic, and selenium. These pairs of elements I've just mentioned will show similar deviations from the general trend of increasing ionization energy. So one of these exceptions we're talking about can be seen when comparing the first ionization energies of the consecutive elements magnesium and aluminium. The reason for this is aluminiums have 3 outer electrons. 2 of them are in a single 3s orbital, and the remaining electron, which is the outermost electron, is on its own in a 3p orbital. Magnesium atoms have only 2 outer electrons, and both are in a single 3s orbital. So the outermost electron for magnesium is this one here, and the outermost electron for aluminium is this one here. So aluminium's outermost electron is therefore higher in energy. When we say higher in energy, we mean further away from the positive nucleus compared to magnesium's outermost electron. Magnesium's outermost electron, like I stated before, is in the 3s sublevel compared to aluminium's, which is in the 3p sublevel. In case you didn't know, sublevels are smaller energy levels which make up the larger main energy level. Magnesium and aluminium have 3 main energy levels, but it is on the 3rd main energy level where the outer electrons are found. Magnesium has 2 outer electrons, aluminium has 3 outer electrons. Both have just 1 outermost electron, obviously, because there can only be 1. But aluminium's outermost electron is in a 3p sublevel, and magnesium's outermost electron is in a 3s sublevel. And again, the greater the sublevel, the higher the energy, or the more energy it has, because the further away from the nucleus it is. So the electrostatic forces of attraction between aluminium's outermost electron and the positive nucleus is weaker than between magnesium's outermost electron and the positive nucleus, because aluminium's outermost electron is further away from the nucleus than magnesium's outermost electron. So aluminium's outermost electron therefore requires less energy to remove compared to the outermost electron in a magnesium atom. So aluminium has a lower first ionization energy compared to magnesium, despite the fact that magnesium precedes aluminium in period 3 of the periodic table and should, according to the trend, have a lower first ionization energy. So now let's look at the second exception to the first ionization energy trend across a period. The second exception can also be seen in period 3 when comparing the first ionization energies of the consecutive elements phosphorus and sulfur. Phosphorus atoms have 5 outer electrons. 5 outer electrons are in the 3rd main energy level, but obviously they're in different sublevels, with 3 in the 3p sublevel and 2 in the 3s sublevel. Each of the 3 electrons in the 3p sublevel are in separate 3p orbitals, and both electrons in the 3s sublevel are in the single 3s orbital present. Sulfur atoms, however, have 6 outer electrons in total, which are also on the 3rd main energy level, with this time 4 in the 3p sublevel and 2 in the 3s sublevel, and 2 of the 4 3p sublevel electrons are in separate 3p orbitals, and the remaining 2 electrons are both in a single 3p orbital, since there are only 3 orbitals in the 3p sublevel and therefore no room for the electrons to spread out, because orbitals have a maximum capacity of 2 electrons and no more. Electrons are negatively charged, and since like charges repel, there is always electrostatic repulsion between electrons on any energy level in all atoms, be it in the main energy level or in the sub-energy level. But the repulsion between electrons in sub-energy levels and in orbitals are greater than those between electrons in main energy levels. These 3 outer electrons in a phosphorus atom are in separate 3p orbitals and are therefore more spread out, compared to sulfur's outer electrons, which have 2 half-full 3p sublevels and 1 full 3p sublevel, meaning sulfur's outer electrons are more closely packed because of the extra electron, so there's therefore greater electrostatic repulsion between them. So we don't have an extra orbital here, so we have to put the extra electron with another electron that's already in an orbital, and that creates extra repulsion between the electrons in the 3p sublevel because they're less spread out compared to electrons in the 3p sublevel sublevel in phosphorus. The greater number of outer electrons in a sulfur atom compared to a phosphorus atom led to the presence of greater electrostatic repulsion because of the more closely packed electrons. This was a result of there being only 3 orbitals in the 3p sublevel, hence why sulfur has a lower first ionization energy compared to phosphorus. So here this yellow arrow shows that we have greater electrostatic repulsion between these electrons than between these electrons. And the outermost electron for phosphorus is this one here. The outermost electron for sulfur is this one here, or it could be this one as well, but it has to be on the 3p sublevel. In case you didn't know, these white boxes represent atomic orbitals. Atomic orbitals are volumes of space in which there is a probability of 95% of finding an electron in that region, and it can hold up to a maximum of 2 electrons. Now let's look at ionization energy trends going down a group. So the trend in ionization energy is for the atoms of the elements going down a group in the periodic table shows a decrease in ionization energy. This is because the atomic shielding, again the atomic shielding is the number of main energy levels. The atomic shielding of the atoms of the elements going down a group increases this time. So now we have increasing atomic shielding, which we didn't have when we looked at the ionization energy trends across a period. The distance between the positively charged nucleus and the outer electrons, and therefore the atomic radius, will therefore increase because of the increasing atomic shielding for the atoms of the elements going down a group. So the strength of the electrostatic forces of attraction between the positively charged nucleus and the outer electrons decreases because the outer electrons are now further away from the positively charged nucleus, again because of the atomic shielding. As a result, the energy required to remove the outer electrons for the atoms of the elements going down a group decreases due to the decreasing electrostatic attraction. So less energy is required to overcome decreasing electrostatic attraction, hence why ionization energies decrease for the atoms of the elements going down a group. The example we have here is group 1. So for group 1 ionization energies, the atomic radius is increasing for the elements going down group 1. Lithium is the first element in group 1. Then we have sodium, then potassium, then rubidium, then cesium, then francium. Lithium has the smallest atomic radius because it has the least atomic shielding, and francium has the greatest atomic radius because it has the greatest amount of atomic shielding. Because francium has more atomic shielding than lithium, the first ionization energy of a francium atom is less than that of lithium because the outermost electron of a francium atom is further away from the nucleus than the outermost electron of a lithium atom. And again, the reason for this is the increasing atomic shielding. The atomic number, I should point out, also increases, but the effect of atomic shielding is far greater than the increase in atomic number, because you may think that, well, the atomic number is also increasing because francium has a way higher atomic number than lithium. So in theory, the higher atomic number should pull the outer electrons closer to the nucleus, but that's actually not what happens because the atomic shielding always has a greater effect than the nuclear charge. This is just a general rule you should follow. So ionization energies actually decrease going down the group and increase going up the group. The trend says atomic shielding increases down the group, so therefore ionization energies increase going up the group. So the ionization energies increase going up the group and decrease going down the group. And here's a graph showing the ionization energies of group 2 this time. So just like the previous graph, we have first ionization energy on the y-axis and the atomic number on the x-axis, and beryllium is the first group 2 element, and then we have magnesium, and then calcium, then strontium, then barium. Generally, we have a trend of decreasing ionization energy. And again, it's for the reasons I mentioned before, and unlike before, there's no exceptions. Now let's talk about the proof of the existence of main and sub-energy levels. So we can use the explanations for the drop in first ionization energies between magnesium and aluminium and between phosphorus and sulfur as evidence for the existence of main and sub-energy levels. In the case of magnesium and aluminium, the fact that aluminium's outermost electron is further away from the nucleus than the outermost electron in magnesium is because of the particular sublevels both electrons are located in, and these are the 3s and 3p sublevels respectively. Magnesium's outermost electron is in 3s sublevel and aluminium's outermost electron is in the 3p sublevel. The 3p sublevel is further away from the nucleus compared to the 3s sublevel. So as we said before, the outermost electron of aluminium is higher in energy compared to the outermost electron of magnesium. So aluminium's outermost electron therefore experiences weaker electrostatic attraction compared to magnesium's outermost electron. So aluminium's outermost electron therefore requires less energy to remove because you need less energy to overcome weaker electrostatic forces of attraction. In the case of phosphorus and sulfur, the fact that there is less electrostatic repulsion between the outer electrons in a phosphorus atom compared to that in a sulfur atom is because all three of phosphorus's outermost electrons Again, just to avoid confusion, phosphorus has 5 outer electrons in total on the third main energy level, but the 3 outermost that I'm talking about are the ones in the 3p sublevel. The other 2 are in the 3s sublevel, so I'm counting the 3 outer electrons on the 3p sublevel as the outermost electrons. So each of these 3 separately fill all 3 3p orbitals within the 3p sublevel, whereas sulfur atoms have 4 outermost electrons. They have 6 outer electrons in total on the third main energy level, and 2 of these, like we said before, 2 of these fill separate 3p orbitals, but the remaining 2 jointly fill a single 3p orbital, since there are only 3 orbitals on the 3p sublevel and the maximum capacity of one orbital is 2 electrons. The fact that sulfur's outermost electrons are not as spread out between the orbitals as those in a phosphorus atom is why there is greater electrostatic repulsion between the outer electrons in a sulfur atom, and therefore why sulfur atoms have a lower first ionization energy compared to phosphorus atoms. So again, the explanations for why there's a dip in first ionization energies between magnesium and aluminium and between phosphorus and sulfur can only be explained using sub-energy levels, orbitals, and main energy levels. There's no other explanation, hence why we can use this as proof of the existence of main and sub-energy levels. Now let's look at some summary questions. So here we have an interesting summary question for you to try, and I picked only one summary question because the others I could find would involve just copying exactly what we talked about in the slide, so I just picked this summary question, and it's an interesting one. We didn't really look at this in much detail, I'd say. Pause the video and try and see if you can answer this question. So state why the second ionization energy of any atom is larger than the first ionization energy. So have a go on this question. So the answer to this question is as follows. The second ionization energy of any atom is larger than the first ionization energy because the second ionization energy involves removing the second outermost electron of an atom. The second outermost electron of an atom is closer to the nucleus. So the outermost electron of any atom is further away from the nucleus than the second outermost electron. So since the second outermost electron is closer to the nucleus, it experiences stronger electrostatic attraction compared to that experienced by the electron furthest away from the nucleus. So more energy is needed to overcome the greater electrostatic forces of attraction between the positively charged nucleus and the second outermost electron than the energy needed to overcome the electrostatic forces of attraction between the outermost electron and the positively charged nucleus. So the answer, as I've written here, says the first ionization energy removes the outermost electron and the second ionization energy removes the second outermost electron. The outermost electron is further away from the nucleus compared to the second outermost electron and therefore experiences weaker electrostatic attraction compared to the second outermost electron. So more energy is required to overcome the stronger electrostatic forces of attraction between the nucleus and the second outermost electron than the energy needed to overcome that between the positively charged nucleus and the outermost electron, hence why more energy is required to remove the second outermost electron. So from this, as a general rule, we can say that the second ionization energy is larger than the first ionization energy, and the third ionization energy is larger than the second ionization energy, the fourth is larger than the third, and so on. Alright then, so this is the general rule. Now let's look at some practice questions. Let's take a look at this question here. The question says, which of these has the first ionization energy? First thing we should do is identify the positions of all these elements in the periodic table. So looking at the periodic table, you can see sodium is here, silicon is there, chlorine is here, and aluminium is there. So all the elements listed in that multiple choice question are in period 3 of the periodic table. And that's a key observation which we will make use of. So atoms of the elements on the same period have the same atomic shielding, and the ionization energy increases across the period from left to right. We covered these in the slides. So the element here which is closest to the right of period 3 is chlorine, and sodium is actually the first element in period 3. So sodium will have the fewest number of protons in its nucleus, and it will therefore have the weakest electrostatic forces of attraction between its nucleus and the outer electrons. So this will have the lowest first ionization energy because less energy is required to overcome weaker electrostatic forces, and chlorine is the element closest to the far right of period 3, so it will have the greatest nuclear charge and therefore the strongest electrostatic forces of attraction between the positive nucleus and the outer electrons. So more energy is required to overcome these electrostatic forces and remove the outermost electrons compared to sodium and compared to aluminium and silicon. Aluminium and silicon are closer to the middle of period 3, but since chlorine is closest to the far right, and we said that ionization energy increases from left to right across any period, not just period 3, chlorine must have the highest first ionization energy. So for this question, we need to write an equation including state symbols to represent the process that occurs when the third ionization energy of manganese is measured. The first thing we should do is identify the chemical symbol of manganese. So here we can see that the symbol of manganese, the chemical symbol, is Mn. So this is the chemical symbol we need to use in the equation. So we need to write the chemical symbol Mn, and before we do anything else, let's determine whether at the start the manganese is an ion or an atom. Question says when the third ionization energy of manganese is measured, and we said before that the third ionization energy can't happen unless the first and the second ionization energies have happened as well. And since the first and the second ionization energies must have also happened, the outermost and second outermost electrons must have been removed from the manganese atom already, and so we're left with a manganese 2+ ion. So it's a manganese 2+ ion. We will start when the third ionization energy of manganese is measured. And then obviously we need to make sure we use the gaseous state symbol, so we write the lowercase g in brackets and then do the same with the product ions. We don't need to write the gaseous state symbol for the electron, and we show an arrow going from the reactants to products as well. So this here is the final answer. We start with the manganese 2+ ion, and we make sure it's denoted as a gaseous ion. And one electron is removed from the manganese 2+ ion to form a manganese 3+ ion, which is also in a gaseous state, and the electron removed is shown here. You need to make sure you denote the manganese 2+ and manganese 3+ ions as gaseous. Now this question here wants us to state which of the elements, magnesium and aluminium, has the lower first ionization energy. We looked at this in the slides. Aluminium has the lower first ionization energy because aluminium's outermost electron is further away from the nucleus of the atom compared to magnesium's outermost electron, since aluminium's outermost electron exists in a 3p orbital and magnesium's outermost electron exists in a 3s orbital. So there's weaker electrostatic forces of attraction between the positively charged nucleus and aluminium's outermost electron compared to the electrostatic forces of attraction between magnesium's nucleus and its outermost electron. So less energy is required to overcome the weaker electrostatic forces of attraction between the nucleus and aluminium's outermost electron than those between magnesium's outermost electron and its nucleus. So here's the final answer. Aluminium has the lower first ionization energy. This is because magnesium's outermost electron is closer to the positive nucleus than aluminium's outermost electron, since magnesium's outermost electron is in a 3s orbital compared to aluminium's, which is in a 3p orbital, and it therefore requires more energy to remove, since more energy is required to overcome stronger electrostatic forces of attraction. You can also use the term higher in energy when comparing aluminium's outermost electron to magnesium's outermost electron. And just one more thing, I believe I may have forgot to mention, these deviations in the trends in ionization energies we looked at in the slides, these particular ones only apply to first ionization energy. They don't apply to second or third. That's a very important point to keep in mind, but you can apply these deviations to, as we said, elements in equivalent positions in other periods. So let's look at this question here. The question says bromine exists as two isotopes, bromine 79 and bromine 81, which are found in almost equal abundance. And it wants us to determine which of the statements is correct. So the option A says the first ionization energy of bromine 79 is less than the first ionization energy of bromine 81. Option B says the atomic radius of bromine 79 is less than the atomic radius of bromine 81. Part C says the mass spectrum of bromopropane has two molecular ion peaks at 122 and 124. Option D says bromine 79 is more reactive than bromine 81. So let's tackle these one by one. So for option A, the option says the first ionization energy of bromine 79 is less than the first ionization energy of bromine 81. Well, that can't be true because bromine 79 and bromine 81 are isotopes, and isotopes are atoms with the same number of protons but different numbers of neutrons. And since they have the same number of protons, they must also have the same number of electrons, because atoms have an overall charge of 0 and isotopes also have an overall charge of 0. So in this case, bromine 79 and bromine 81 will have the same number of outer electrons, therefore the same electron configuration and the same number of protons. So it's therefore unreasonable to say the first ionization energy of bromine 79 is less than the first ionization energy of bromine 81. Part B says the atomic radius of bromine 79 is less than the atomic radius of bromine 81. This is also not true because the atomic radius depends on the nuclear charge, and the nuclear charge of bromine 79 is the same as the nuclear charge of bromine 81, and the reason for that is, again, they're both isotopes. Isotopes always have the same number of protons. It's just the number of neutrons that differ, but neutrons have no charge and therefore have no effect on the nuclear charge and no effect on the atomic radius or ionization energy. We'll come back to option C in a moment, but option D says bromine 79 is more reactive than bromine 81. Reactivity depends on a number of factors. It depends on atomic shielding, nuclear charge, and how many outermost electrons there are. Bromine 79 and bromine 81 have the exact same nuclear charge, the exact same amount of atomic shielding, and the exact same number of outermost electrons. So it is unlikely bromine 79 is more reactive than bromine 81. That leaves us with only C, which is the reasonable option. C says the mass spectrum of bromopropane has 2 molecular ion peaks at 122 and 124. And this seems reasonable if we were to do the calculation, so find the MR of bromopropane using both isotopes, so doing the first calculation with bromine 79 and the second one with bromine 81. It's very likely we'll get mass spectrum peaks at 122 and 124 because of the different isotopes. The difference between 124 and 122 is 2, just like the difference between 81 and 79. The difference is also 2. So the answer to question 25 is C. So this brings us to the end of the video. I hope you found this video useful. If you have any questions, please post them in the comments. I would be more than happy to help. You can attempt more questions like these down below in the video description. If you find these videos useful, please consider subscribing, and more videos like this will be coming soon. So thank you for watching and see you next time.